So we will show how the radian measure of an angle came about. Coming from degree measure, how can we produce the relationship between radian measures and degree measures? So let's say, for example, we have angle BCA. How do we produce an angle with a particular degree measure? Well, starting from the initial side, we can rotate our angle counterclockwise. So if we want to produce a 90-degree angle, we rotate it in such a way that the terminal side will coincide with the vertical axis. So this one is an angle whose degree measure is 90 degrees. When our rotation is counterclockwise, we interpret it to mean a positive angle. When we rotate our angle clockwise, we interpret it to mean a negative angle. But this software, this is GeoGebra. GeoGebra does not register a negative angle. It is only showing the measurements in positive value. Okay, so that is how we produce an angle in standard position. Okay, so what I'm going to do next is I will write a unit circle in this rectangular coordinate system. So this is a unit circle. And let us show the equation for this circle. You know the equation of a unit circle whose center is at the origin. It is x squared plus y squared is equal to 1. You know what? I kind of miss our discussions in conic sections. We talk a lot about conic sections, and the circle is one among them. Okay, if I were now to rotate the terminal side of our angle, the terminal side of our angle would always have a point of intersection with the unit circle. And let us call that point D. As we move the terminal side of our circle, that point of intersection is also moving together with the terminal side of our angle. But you know what? As we rotate the terminal side of our angle, that rotation is actually tracing an arc in our unit circle. And that arc has a corresponding length. Look at this, okay? So if I were to make one complete revolution, that would trace an arc whose length is equal to, so what do you think? If I were to make one complete revolution, 360 degrees, what would be the length of the arc? Well, the length of the arc would have to be 2 pi. It would have to be 2 pi because this is a unit circle, and you know how to compute for the circumference of a unit circle. It is equal to 2 times pi times 1. So we have a working ratio here, okay? One complete revolution, which is 360 degrees, is to 2 pi or 2 pi radians. What if our revolution is 1/2 of a complete revolution? So that rotation would trace an arc in our unit circle whose length is equal to 1/2 of the full circumference of a unit circle, which is equal to pi. So 180 degrees in degree measure is equivalent to pi or pi radians in radian measure. What if our rotation is only 1/4 of a complete revolution? So if it were 1/4 of a complete revolution, in degree measure that is 90 degrees, but in radian measure that is only pi divided by 2. Now what if our rotation is 3/4 of a complete revolution? Okay, so in degree measure, that's going to be equal to 270 degrees. Okay? But the arc, the length of the arc that it traces in our unit circle has a length that is equal to 3 pi over 2. What if our degree measure is 0? So if our degree measure is 0, then the radian measure of our angle or the length of the arc that it traces is also 0. So you can see here now the working ratio between degree measures and a radian measure. And I think that you can see now that it is perfectly logical to jump from degree measures to radian measure, because as we rotate the terminal side of our angle, that rotation is actually tracing an arc with a particular length. And these are the working ratios. 360 degrees is to 2 pi, okay, one complete circumference of a unit circle. 1/4 of a complete revolution, which is 90 degrees, is pi over 2. Half the circumference of a unit circle, which is pi, in degree measure, that is 180 degrees. And then 3/4 of a complete revolution, which is 270 degrees, in arc length of a unit circle, is equal to 3 pi over 2.